Welcome to Learning Outcome 3, where we explore correlation, how we tell whether two things move together. We'll measure it, picture it, and crucially, learn why it never on its own proves cause and effect. Bivariate data just means we record two variables for each item, like revision hours and exam mark for each student. Correlation is about whether those two variables are related and how strongly. We're looking for a pattern. As one goes up, does the other tend to go up, or down, or neither? But here's the health warning we'll keep returning to. Correlation on its own never proves that one variable causes the other. Correlation comes in three flavors. Positive correlation is when one variable rises as the other rises, like hours studied and marks achieved. Negative correlation is when one rises as the other falls. Think price and quantity demanded, or a car's age and its value. And no correlation means there's no clear relationship at all, just a shapeless scatter of points. Direction is the first thing to read off any relationship. A scatter diagram plots one variable against the other, 1 point per item, and it's the quickest way to spot correlation. Points that rise from left to right show positive correlation. Points that fall from left to right show negative. A shapeless cloud with no drift means little or no correlation. And there's a second dimension too, strength. If the points hug an imaginary line tightly, that's strong correlation, whereas if they're widely scattered, it's weak. Direction and strength together tell the whole story. A few rules for drawing one well. Put the explanatory variable, the one you think does the influencing, on the horizontal axis, and the response variable on the vertical. Choose a sensible scale so the points fill the graph, and the pattern is easy to see. Plot each pair of readings as a single point, and never join them up. Then, before you draw any line, just look at the overall shape and ask whether the trend is roughly linear. If the trend does look linear, we summarize it with a line of best fit, a straight line passing as close as possible to all the points. You want roughly equal numbers of points above and below it, and here's a reliable check. The line should pass through the mean point, X bar, Y bar. Once drawn, it captures the trend and lets you estimate one variable from the other. Software can work out the exact least squares line, but at this level, a well-judged line by hand is perfectly acceptable. Let's see one at work. We plot 10 students' revision hours against their test marks, and the points climb clearly from left to right, a strong positive correlation. We draw the line of best fit so it runs through the mean point, X bar, Y bar. Working out its equation gives roughly Y equals 5.3 X plus 25. That equation quantifies the trend, and now we can read estimates straight off the line. Let's use that line, Y equals 5.3 X plus 25. First, estimate the mark for a student who revises 8 hours. 5.3 times 8 is 42.4, plus 25 gives 67.4, so about 67%. Now go the other way and find the hours needed for a target of 60. Set 60 equal to 5.3x plus 25, so 5.3x is 35, and x is 35 divided by 5.3, about 6.6 hours. Both of those sit inside the range of our data, so this is his interpolation, which is reasonably safe. Just remember, estimates are guides, not guarantees. Real results scatter around the line. That word, interpolation, deserves a proper look. Interpolation means estimating within the range of data you actually collected, and it's generally reliable. Extrapolation means estimating beyond that range, and it's often anything but reliable, because the pattern may simply not continue outside what you observed. If your revision data only went up to 11 hours, predicting a mark for 40 hours is a real leap of faith. So always state clearly whether an estimate is interpolation or extrapolation. Here's a vivid example of extrapolation going wrong. A baby's weight climbs steadily over its first few months, giving a lovely, strong, positive line. Within that first year, the line predicts weight really well. That's interpolation. But extend the very same line out to age 20, and it would predict a weight of hundreds of kilograms, which is obviously nonsense. The linear trend just doesn't continue. Growth slows and eventually stops. It's a memorable reminder to trust a line only across the range of data used to build it. Now the big one. A strong correlation does not prove that one variable causes the other. There might be a third factor, a confounding variable, quietly driving both. Or the whole thing could be coincidence, which happens surprisingly often in small samples. To actually claim causation, you need controlled evidence, typically an experiment, not just a suggestive scatter graph. Hold that thought, because the next slide shows exactly how a correlation can fool you. Across the summer months, ice cream sales and cases of sunburn both climb together, giving a strong positive correlation. But it would be daft to conclude that eating ice cream causes sunburn. The real culprit is a third variable, hot, sunny weather, which pushes both up at the same time. That's a confounding variable creating what we call a spurious correlation. The correlation is genuinely there in the numbers, but the causal story is false. So always ask what else might explain a relationship before you claim cause and effect. Eyeballing a scatter graph is fine, but we'd like a single number for the strength and direction of a relationship, and that's a correlation coefficient. It always lies between -1 and +1. +1 is a perfect positive relationship, -1 a perfect negative. A naught means no linear relationship at all. Values near plus or -1 mean a strong relationship. Values near naught mean a weak one. The one we'll compute by hand is Spearman's rank correlation coefficient, which works from the ranks of the data. Spearman's coefficient, written R sub S, compares the rank order of the two variables rather than their raw values. Step 1. Rank each variable separately, say from highest to lowest, being consistent. Step 2. For each item, find the difference d between its two ranks, then square it to get d squared. Step 3. Apply the formula R sub S equals 1 minus 6 times the sum of d squared divided by n times the quantity n squared minus 1, where n is the number of pairs. It looks fiddly written out, but it's very quick once you're filling in a table. Let's set up that table for 6 students, ranking revision hours and marks 1 to 6. Student A tops both, 11 hours and 83 marks, so rank 1 on each. Student F sits bottom on both, 3 hours and 41. For each student, we take the difference d between the two ranks and square it. Because the orders match so closely, those differences stay small, which already points towards strong positive correlation. Now we just total the d squared column and feed it into Spearman's formula. Now the calculation. With our 6 students, we work out d, the difference in ranks, and d squared for each. Then total them. The sum of d squared comes to 2. With n equal to 6, E(on) times the quantity, n squared minus 1, is 6 times 35, which is 210. So R sub S equals 1 minus 6 times 2, divided by 210. That's 1 minus 12 over 210, which works out to 0.94. An R sub S of 0.94 is very close to +1, so that's a strong positive correlation. So what does 0.94 actually tell us? It confirms what the scatter graph hinted at. More revision goes hand in hand with higher marks. As a rough guide, values from 0.8 to 1 are strong, 0.5 to 0.8 moderate, and below 0.5 weak, and that applies to negatives too. A coefficient near naught means no monotonic relationship, though not necessarily no relationship whatsoever. There could still be a curve. And always report the sign as well as the size. Minus 0.9 is every bit as strong as plus 0.9, just in the opposite direction. There's a second coefficient worth knowing, Pearson's product moment correlation coefficient, usually just called R. It measures linear correlation using the actual values rather than the ranks. Like Spearman's, it runs from -1 to +1, with the same reading of strength and direction. Spearman's is easier by hand and copes with ranked or non-linear but still monotonic data. Pearson's is the one you'd prefer when the data is roughly linear and measured on a proper numerical scale. Let's put correlation to work in business. A shop compares its weekly advertising spend with sales revenue over 8 weeks and finds an sub S of 0.82. That's a strong positive correlation. Weeks with more advertising tended to see higher sales. The manager could use the line of best fit to estimate sales for a planned advertising budget. And you knew this was coming, correlation isn't proof. Seasonality or price changes might also be driving those sales. The sensible move is to test the link, perhaps by trialing different spends and measuring what happens. A few limitations to keep in mind. A correlation coefficient only picks up a consistent trend, so it can completely miss a curved, non-monotonic relationship. Outliers can distort the result, and Pearson's R is especially vulnerable to them. A small sample can throw up a high coefficient purely by luck, and once more for the back row, correlation never on its own establishes cause and effect. The golden rule: report the coefficient alongside the scatter graph and the sample size, and never claim causation from correlation alone. Let's draw learning outcome 3 together. Correlation describes the relationship between two variables, and scatter diagrams reveal its direction and strength. A line of best fit passes through the mean point, x bar, y bar, and lets us estimate one variable from the other. Interpolation within the data is reliable, whereas extrapolation beyond the data can produce absurd predictions. Correlation is not causation, since a confounding variable can manufacture a spurious relationship. And Spearman's rank, R sub S, equals 1 minus 6 times the sum of D squared over n times the quantity n squared minus 1, gives a number from -1 to +1 for the strength and direction of the link. So, there's correlation. Easy to picture, quick to quantify with Spearman's rank, and forever needing that caution about causation. To take it further, Crawshaw and Chambers works carefully through both Spearman's and Pearson's coefficients, and the Royal Statistical Society's Significance magazine has some genuinely entertaining pieces on spurious correlations. Corbett Maths is handy if you'd like more worked practice on scatter graphs and lines of best fit. Have a go at ranking a small data set of your own and computing R sub S by hand. That's the fastest way to make the formula stick.